Hi, welcome back. This is the last video on this amazing book, Rocket Propulsion Elements. Again, book club, go read this, go dig in, dig into the engineering, dig into the homework problems. This is really a book. I'm just trying to hit the wave tops as kind of a review and help guide you through this path as you kind of go learn yourself. Again, this is a great book, great way to kind of read and learn all of the basics of rocket propulsion, and not just the basics. I'd actually say this book is kind of giving you a lot of the exposure to the real systems, real challenges, the real things you'll have to face as an engineer if you're out there working with these amazing engines. Okay, and so last couple chapters here as we kind of wrap up. The first one, and we've already talked about it a little bit, but the first one is actually on this is chapter 18. It's on thrust vector control. Now I got to tell you, the number of times I've had to catch myself from not calling this gimbaling, okay? Because at most rockets gimbal. That's how they do these thrust vector controls. So they just gimbal. Okay, and gimbal is actually they literally have arms that are shoving the rocket around. Now sometimes it can be driven electrically. I believe Raptor engines are electric driven. At Virgin Orbit, our gimbal system was driven fuel hydraulically, so it was a hydraulic system, but using fuel, not hydraulic liquid. And then those are kind of the ones that I'm used to in the rocket world. But certainly there are a whole other broad ones. So I actually, again, I hope I don't do it on the video. I'm going to be trying really hard to call it thrust vectoring control based on all the other flavors that you can actually do to deflect the plume. Okay, and this is all about a couple of things, a couple of reminders. There's alignment. So there's guaranteed your rocket engine's not going to be perfectly pointed straight back. Okay, perfect doesn't exist. You're always going to have the deflection. And that deflection can be half a degree. And that really stacks up. Okay? This is, rocket, a half degree will eventually completely turn over and you're done. So this is, you have to have a way to control and adjust for it. Now, in addition to that, you can get, if you're SpaceX and you're trying to land, and I've seen the Starship landings, I mean, it's a 30-degree gimbal in order to have that much control authority on how to really kind of move the vehicle around. So it can be pretty large. And at Virgin Orbit, right, we dropped off the wing of a 747, and so our first thing we had to do was sort of count to 5 as the 747 was banking away and then execute a pretty gnarly pull-up maneuver. And so I think our gimbaling was up to like 8 or 10. So it was that'll be not normal. A normal vertical rocket launch would only need to gimbal up to 3. But those are all gimbaling. So there's really a broad range. So I've got some pictures here. There's gimbal, okay, the broad range. But a lot of the solid rocket motors can actually do the next two. Okay, the flexible laminated bearing, where it can kind of you move it back and forth. So the gimbal is a hinge, okay, versus where here your motor, okay, so usually the solid rocket motor is not moving, but you're just moving the nozzle. So a couple different ways to move the nozzle. Okay, and then you can have that flexible nozzle joint. Oh, that's flexible laminated bearing. But then you can also have jet vanes. I actually know a company that's doing jet vanes. They've now qualified it. Their exhaust is a little lower in temperature. I'll remain quiet who it is, but they got vanes working. I was like, oh, that's pretty cool. Like there's things you can do when your exhaust temperature is a little bit lower. Okay, that's literally where you have an airfoil in the stream. You might have 2, you might have 4. You would need at least 2 to provide control, but sometimes 4 are a little more balanced. Okay, so it's for just alignment. I better finish this alignment, but it's also control. And so a normal rocket will, yes, it'll start pointed straight up, but actually it then kicks over. What you're trying to do is climb, get a good rate of climb going to get out of the soup, but ultimately orbit it sideways, right? 5 miles per second or 8 kilometers a second sideways. And so there's just control that you need to go do. Okay, so that's kind of I'd say the basic 4, but you can continue on. Okay, it's a jet evader, which is a rotating airfoil shape, so you kind of keep rotating around. You can adjust it. Jet tabs, so as opposed to airfoil that's deflecting, this is literally just adding drag on one side or the other. Okay, that's simple, but a fairly easy way to do it. And here you say that they kind of rotate in and out, so you're not always cooking them. Side injection. Now this one's actually interesting from at Venus says rotating detonation. So it doesn't, side can mean, in this case it's coming from your nozzle. For us, side could actually be the aerospike. where you're actually injecting a secondary fluid on one side, and that's enough to sort of deflect a flame. Okay, and then the other one is just carry something else. Okay, you could keep your rocket engine fixed and bolted, and then you could have smaller thrusters that are on and doing it. Now, I will say at Virgin Orbit we used as is common in a lot of gas generator exhaust, that you don't just dump the exhaust. You can actually have a little bit of thrust of that exhaust, and you can also use that for some control. Okay, it doesn't always get you fully away from, say, gimbaling, but you can get some control with where you point that exhaust. Okay, so those are kind of the big ones on thrust vector control, the big eight. And so good description on each one of those. They kind of, this chapter, while it's a standalone chapter, they actually discussed a lot of this sort of kind of all throughout the book as we were talking about different pros and cons of different systems. So it's been touched on, but here it's just sort of fully there in one chapter. Chapter 19, I actually really appreciate chapter 19. It's just on the system traits. And, the authors have been doing a good job of writing throughout the book the system traits as well. But again, it's nice just to have, you can go just boom right here, and you can see all of the system traits. And as I've sort of said multiple times, I do get annoyed at how many people, engineers will forget the system level. And so I'm just going to kind of write the thing that I did in some of my Kuchaman videos, where just as an example, so you have the weight of your total system, which is the weight of your structures, plus your weight of any auxiliary systems, avionics, what have you, plus, weight of your payload, plus weight of your engine, plus weight of your propellant, okay? My orange is flaking out of here. I'll switch back to yellow. All right, and then if you divide by W, what you get is 1, and then I'm actually going to combine these two. And this, following the Kuchaman method, basically there's a vehicle level structure and system stuff, just some coefficient, less than 1, okay, some coefficient. And then payload, so this is now P as a payload fraction, and then 1 plus C2, where this coefficient 2 is actually the structures and systems to hold the payload. And this can be like 1, okay? A lot of times it's if I'm a rocket trying to carry 100 kilograms, it's going to take potentially 100 kilograms of stuff to keep the payload secure and happy and cooled. If humans are your payload, like on an aircraft, like it can be more. Like the humans need air to breathe. You got to have pressurized cabin. You got to have heaters. You got to have seats. You got to have drinks. Okay, so C2 can build up. Engine. So usually what you do here is you say this is sort of thrust to weight of the vehicle, and then divided by thrust to weight of the engine. So you can see the thrusts sort of cancel out, and then the weight of the vehicle was there. So this is what happens. Now on a rocket, as a reminder, the thrust to weight of a rocket may be 1.1, but also the thrust to weight of something going supersonic, wearing my Venus hat, usually you got to be 1.1 to get through the over 1 to get through the sound barrier. So it's the same number whether you're trying to be a supersonic aircraft or a launch vehicle. The challenge here is that a jet engine has a thrust to weight of 7, and a rocket engine may have a thrust to weight of like 50 to 100. And so, ultimately your weight of your engine, weight of your rocket engine is a lot less than the weight of a jet engine. Okay, and then you have your propellant. The propellant mass fraction is usually listed as a lambda, and then you can have 1 plus. Oh shoot, there's a 1 plus C3 here as well. It does take structure and systems to hold your jet engine, and then 1 plus C4. And this is the one that really kills me, where people completely forget that this is highly a function of density, okay? Average propellant density. And that's this chart you've seen me flash up a couple of times. That basically incorporates all of this. Honestly, this thing is just the rocket equation. It's just a rocket equation where you account for C4 here, okay? Where you account for what it takes to hold that. And so that's why, and you heard me talk about last video, nuclear thermal rockets isn't great. That's at 1200K. 2400K is up here. It's still not great. This would be getting to orbit, but the delta V's here would be equivalent to if you're trying to have a nuclear reactor doing laps to the moon without aero braking around the Earth. It's this almost the same curve, okay? And so there's your LOX hydrogen. We talked about this before, that space shuttle main engine is way more better performing, but with this kind of density, you had to carry the big fat orange tank. So it actually, in the end, it's the same payload to orbit as going, LOX RP or LOX methane. LOX methane has a little bit of an advantage there. That's where you're seeing some people switch to it. As we've talked about before, there's other reasons to switch to it. So that's kind of the weight system trade that I get frustrated when I see a lot of people sort of forgetting to account for all these things. It's not just ISP. And again, when I mentioned the electric stuff last video, again, electric a lot of times sort of ignores. There's a third axis there of weight in the engine that usually gets ignored at those levels. That not at the system level when you're trying to solve for all of it. So that's important. So it's a great chapter. Go read it. Like honestly, go read it. There's a lot of discussion there, sort of all the things that stopped in the previous chapters, bringing it back. It's really quite good. Okay, and then chapter 20 is actually a pretty neat discussion on exhaust plumes. Okay, I didn't go back and look at sort of the history of all the additions, things like that. This feels to me like a separate, like they probably added it at some point as a separate discussion that might not have been in like the first or second edition. I'd have to go look. Didn't. But there's just, there's some beautiful pictures out there of some great exhaust plumes. So I'll just show you, when you see these shock diamonds, okay, what's actually happening is usually it's a rocket engine that your nozzle is designed to work at higher altitudes, but you're at sea level. So what happens is here you're actually low pressure, and that's going to create a shock wave, and then the atmosphere is going to kind of push back in. And so everything basically, if you're sonic at the throat, you're then basically you become sonic again here. And so the flow is kind of turning, but now your high pressure is you got sort of over compressed, and so now you re-expand through all of these kind of shock waves, and then it turns back. And so it makes for a really beautiful, these kind of shock diamonds. But the discussion itself goes into, beyond this, it actually goes into not just the shape, okay? So we'll talk about the shape, but it'll also talk about things like smoke and vapor. So good discussion there. If from a spacecraft, you actually do have to worry about coating. So coating on panels, right? If your engine is firing, and some of that exhaust plume may kind of get back to your solar arrays. Again, you're not thrusting very much, you're not moving that very far. And so that exhaust plume could, especially if it's electromagnetic, could actually circulate back, kind of following some of the magnetic field lines you got to watch out for. Or you just could be, exhaust in general that maybe you have a constellation, and if you're doing orbit shifts, you may not be affecting yourself, but you could be affecting some other satellite in the constellation you got to pay attention to. Okay, so that can add up. And then with solids, the aluminum in solids can actually create comms and radio issues. Okay, there's always there can be some unburnt aluminum in the solid rocket motor, so you got to pay attention to that too as well. So a good discussion, like I said. They talked about some of the stuff in the past, but this is a good kind of complete one, a little more detailed on exhaust plumes. And then, it finishes up with testing. And testing is one of the most important parts. This is the rubber meets the road prior to launch. So really, it's hard to underscore the importance of testing. We do it here at Venus all the time. We sort of engine testing, and then we go do flight testing. What you're seeing here is a stage test. Now, what's happening is you build your entire stage and you're holding it down. Now, it's a hot topic in the rocket launch industry. Effectively, everybody kind of goes and does it. The point of the test is like, whose test is it? And what's funny there is the propulsion team is like, well, we already ran our rocket engine, for a full mission duration. We don't need this. A lot of things you may be trying to do here is actually adjust your pressure to sort of backfilling your oxidizer and your fuel, but you're backfilling at a 1G condition, whereas this rocket is going to be flying, starting off at, accelerating at 1.1 Gs, and then ultimately getting up to 5 or 7. So it's not 1-to-1. It's actually, anyway, that's some hard systems analysis there. But really, it's still it's an all-up round test, right? It's actually the things that can go wrong here, and they do. Okay, things that can go wrong here are still cheaper than, say, a full-up launch failure. So even this is a can be considered a very expensive one-off test, if you will. Like you don't usually test every stage. This is sort of a development test. it then be worth it. Now, a lot of rockets will, when they kind of get fully assembled at the launch pad, will do a very quick version of this, kind of a quick burp. That's very different than their sort of full duration test. You can see here, this actually, the rocket engine is shooting down onto a ramp, and that ramp has got a ton of water kind of blasting through it to keep it from melting. So all I can say here is, yes, important, go do it, and some good discussion there on testing. And what happens, there's another aspect here, I'll just call it, say, design for test. There are aspects of your vehicle or your engine that will change because you need to go do a test like this, or because you need to be able to get test data from an engine. So it's a reality, right? It's there. You might have heard for design for manufacturing, or design for operations, or design for maintenance. There's also design for test. So good chapter on test. Also feels like an addition towards the end, but I love testing, so it was a good chapter to kind of get into. Okay, actually the last thing I'll mention here is it's also designed for failure. And this means a lot of times on a launch, there are things you can only test in flight on a launch. And historic rocket launch success rates is about 50%. Okay, so actually props to Blue Origin, who just did their initial launch and got all the way to space. They didn't stick to the booster landing, but they got all the way to space. That's actually, one on the positive side of 50%. And so you're going to have systems fail in flight. I'm just going to wear my rocket hat for a second. Okay, you're going to have systems fail in flight, and the most important thing is that you're getting the telemetry, and then you're getting enough telemetry from this flight vehicle back that if something goes wrong, you can figure it out. And there's entire failure investigations and systems and fish trees and all these things that you will go through to figure out root cause analysis, to try and not be a human and just race to the one answer, to make sure you've really covered all of the possibilities, you've thought about all the failure modes. And usually what ends up happening when you go do one of these failure modes, you'll come to a likely candidate. It may not be a smoking gun. You'll come to a likely candidate. But invariably what happens after a failure like this is you actually identify 3 or 4 others that could have been it, and you realize you didn't have a great mitigation for those as well. And so you actually, when you kind of rev your vehicle to do the next thing, you sort of take care of the glaring most likely, but you actually take care of some of the other ones too. Not necessarily just from a just in case, but also it's amazing what failures do to sort of retrospectively highlight maybe a few things that were weak in the design, that you only, for some reason, we only achieve it. It's just historically, it's just humans being humans, that usually only comes to light after a failure. Okay, so this is just to kind of conclude. This is a great book. Go dive in and read. It's been a blast going through this. Again, one of my favorites. And so again, if you like in the book club, again, I'm trying to do here is just provide the wave tops, take some great textbooks that are out there, read them. On some of them, I'm going to be experts. Others I'm not. I'm actually just like you, reading to learn and doing the work. So keep reading, keep doing the work, and we'll see you on the next episode.